listen-only mode.
Good afternoon. I'm Julie Blomquist. I'm with the PASS DBA Virtual Chapter, and today we are having a topic: demystifying data warehouses, detecting DW patterns and implementing them with SQL Server. Kevin, is it Goff or Goff? Sorry, Goff will be doing the presentation. The DBA Virtual Chapter is being sponsored by Dell, and they are the ones who assist us so that we are able to do the raffle at the end. Here is a list of some upcoming SQL Saturday events. This is a one-day free education. I think the only fees involved are to cover your box lunch. There's quite a plethora of virtual chapter meetings coming up. Here are just a few. And we do have a SQL 2014 launch webinar series. There's still a couple sessions left on that one. Here is the list of all the different virtual chapters. You would just go to your PASS membership and add the virtual chapter to your membership, and then you'll receive the emails about the meetings. If you're interested in volunteering for PASS, there's quite a few different ways you can do that, and we also are trying to recognize outstanding volunteers. The PASS Business Analytics Conference is coming up May 7th to the 9th over in San Jose. If you register, you can use the code at the bottom there, DBAVC08, and that will give you an additional discount. Here's information about how to stay in tune with PASS. And here's all the information about Kevin. Let me shrink this. He's a Microsoft SQL Server MVP, a database architect, developer, speaker, and author, and a regular columnist for the Code magazine on .NET, SQL Server, and business intelligence topics, and a frequent speaker at the community events in the Mid-Atlantic region. He's the host of BDBI Radio and a weekly webcast on SQL BI topics. This presentation is being recorded. It will be uploaded to the PASS DBA VC archive section, and Kevin is also sending me the slide deck, so I will also be uploading that. Kevin, make presenter. So Kevin, I'm making you the presenter.
Okay, and just want to make sure you can see my screen okay.
Yes, I can see it fine, and we will be doing the questions at the end of the presentation.
Right. Okay, I'm okay to get started.
Yep.
So, okay, great. All right, good afternoon, everyone, or good morning, depending upon what part of the area you're from. And thank you for attending. My name is Kevin Goff, and we're going to talk today about data warehouse patterns using the SQL Server Business Intelligence tools. Now, I frequently in presentations and in articles that I write and in webcasts, I use a baker's dozen theme of 13 different productivity tips, something I've been doing for quite a long time, and actually do SQL and BI webcasts. You just go to bdbiradio.com and check out some of the available webcasts that I've done in the past. Just a very quick introduction on me. As Julie said, I'm a SQL Server MVP. I've been involved in writing a couple of books. The only thing you need to write down here, since the slide deck will be made available to all the attendees, my email address, if you want to contact me with any questions, any follow-up topics, my email address is kgoff, K-G-O-F-F, at kevinsgoff.net. That's kgoff at kevinsgoff.net, and I'll put that back up here at the end of the presentation. As Julie said, I generally like to take questions at the end. Not that I'm not interested in taking questions, I certainly am. Almost every session I do, there usually are a handful of questions that ultimately become content for for a future version of a presentation because somebody's got a really good idea on something. But given the amount of material that I want to get through in the course of an hour, I want to devote all the time for that, and then I'll take questions at the end. And I'll hang around past 1 o'clock for however long we need to for any questions that people have. Now, again, today's topic is 13 tips for data warehousing with SQL Server and BI tools. Now, when I proposed this session to Sharon Dooley a couple of months ago, conversation came up on the interest in how applicable this topic would be to people whose primary jobs are on the database administration end. Well, depending on the type of environment you're working with, sometimes DBAs, actually quite often DBAs, have to double up on time over in the application realm. And so while they're dealing with replication and backups and physical storage and things like that, they also get involved with the ways that the data is being used for line of business applications. And so having awareness, having knowledge of some of the key methodologies in the data warehousing realm are very, very important. Now, one of the reasons that I like data warehousing so much, and one of the reasons why I actually sort of did a career change a long time ago, I used to be a .NET developer, but really was a data guy at heart all along, and switched over to the data warehousing world, is because it's very much like running a medical practice or another type of practice. There are many methodologies that are in place, many patterns, sometimes not immediately recognizable. And so one of the great things about the data warehousing world is there's still a lot of room to make knowledge available about how you can apply patterns to different types of solutions. Now, this presentation is actually based upon an article I wrote in Code Magazine a long time ago. I've got the link for it. I've added to the presentation since, but if you want to go back and read how this whole presentation actually started a few years ago, I've got a link to an article that I wrote in Code Magazine on this very topic. Now, if you haven't already done so, this is one book that definitely recommend that you go out and buy and read at some point. And many of you are probably familiar with this already. It's a data warehousing toolkit by Ralph Kimball. One of the fantastic things about this book is that it's not a book about technology per se. It's a book about methodologies. This book was, the core material was written back in the 2002 time period. And even though there's been a subsequent update to the book, about 98% of the text that was written back in 2002 is still applicable today. Maybe just a few areas where the technology has changed since then, but it's not a book about SQL Server or about Oracle. It is about building data warehouses, and many of the rules, many of the methodologies haven't changed. Again, more recent versions of the book add some additional content, but even if you get the second edition, which was published well over 10 years ago, most of it is still applicable today. So I've got an Amazon link here if you want to take a look at it. And also, I want to reference the Kimball Group website. Ralph Kimball and his group have a fantastic website. Let me pop it up here just very briefly. Here's a website that has a lot of design tips, a lot of training courses, white papers, some references to the consulting practice that he has. You could spend hours and days up here just going through all the other content that he's got. I want to call attention to the design tip area. He's got design tips going back many, many years. Actually, if I go down here and take a look at the archives, he's got design tips going back to 1995. And there have been some very good ones over the years. For instance, in 2008, Ralph Kimball had a very, very good topic about using the T-SQL merge statement for handling slowly changing dimensions. So this one, if you're dealing with updating dimensions, and if you want to see how you can incorporate the T-SQL merge statement, which was added in SQL Server 2008, this is a very good design tip to read. Also, a design tip about the fundamentals of fact tables, about maintaining dimension hierarchies. This is must reading if you work in this particular area. So the topics for today in the Baker's Dozen 13-tip format, the topics for today, these are grouped into a couple of sections. The first two, I'm going to talk at a very, very high level about the goals of a data warehouse / analytic database. And I'll explain in a minute why I've sort of have multiple terms up there. And some of the major components, some of the things that we absolutely must have in any data warehousing project, in any data warehousing endeavor. So those first two topics are going to be a pretty high level. We're going to set the stage for some more detailed level topics as we get a little bit further. We're going to take a look in topics 3, 4, and 5 at the different types of fact tables that are in a data warehouse. Now, first of all, before I go any further, a data warehouse physically is made up of fact and dimension tables. You might have other database constructs in there as well, but you're going to have fact and dimension tables. Now, there are rules about what constitutes a certain type of fact table, the contents that are in it, how you populate it, how it's tied to events that go on in the business. So we'll talk about those. And again, there are 3 different types. There are cumulative, transactional, factless fact tables, and what we call periodic snapshot fact tables. And there are specific rules that that govern which fact table it's going to fall under as far as the category. Then we're going to look at dimension tables and the different types of information that we might have in a dimension table and why they're important. Well, data warehousing, in addition to building fact and dimension tables, is constructing the relationships between them. Now, sometimes fact and dimension tables relate to each other in a very simple and a very clean way. Other times, because of the nature of the data, because of business processes, because of relationships, sometimes fact and dimension data don't necessarily come together cleanly, or it might not be obvious. So that's where we get into some of the nitty-gritty of dimension modeling. And we're going to take a look at the different ways that the fact and dimensions come together. We're going to look at what's called role-playing dimensions. We're going to look at junk dimensions. We're going to look at a special type of dimension known as an outrigger. We're going to take a look at many-to-many bridge tables. Now, some of these you might see in transaction database applications as well. So there certainly is some overlap between a data warehouse and what you might see in a transaction database, and a many-many bridge table is one example. Then we're going to look at Type 2 slowly changing dimensions. Now, you could spend an entire hour and a half, as a matter of fact, you could probably spend an entire day talking about some of the gotchas and some of the specifics of Type 2 change in dimensions, but at least going to give an overview. And then at the end, I'm going to talk about some of the big don'ts in building data warehouses. Now, that one again could be an entire list. We're going to take a look at 2 in particular, and that's the handling of null values and the storing of calculation ratios in fact tables, and why it's not a good idea to do so, and what I'm going to offer as an alternative. So these are the topics we've got here today. And again, the first 2 I'm going to talk at a very high level, then I'm going to get down into more specifics. Well, the goal of a data warehouse, ultimately you are building a warehouse for some specific reasons, and certainly one of the big reasons is that people want to have one version of the truth to look at some of the key metrics within a company's data, and I'm going to use the magic word here, by some of the common business entities. So you could walk into 10 different companies and see 10 different statements here, but they're all going to follow a basic pattern. A manufacturer might want to look at orders by tons, or maybe by pounds, or maybe by other volume metrics available. They want to look at defects into the manufacturing process. Not everything goes perfectly. We might have defects, irregulars, damages, shortages. We might want to look at the amount of material that's going through a regrade process. We might want to take a look at reworks. There are a variety of different metrics that we might want to roll up. And notice how I don't have anything in here for dollars. Well, certainly if you're in a financial environment in a retail database, you want to look at order dollars and sales dollars and return dollars and profit by different business entities. Now, the data at the top here, orders, production tons, dollars, whatever, those are what we refer to as measures or facts. Well, measures and facts need a business context, and that's where dimensions come in. Now, if you ask your users, what are your business dimensions, well, they're probably going to look at you like you're a little bit crazy because they don't think in that technical term. But if you ask people how they look at dollars by, do you look at dollars by this, by that, then the light bulb comes on, because that's how business people think. They look at data by customer, by material type, by some of the dimensions of the material that's sold, by salesman, by time period. Certainly any database is going to have the ability to look at data by year, by quarter, by month, by whatever time period you happen to have. Now, there are people who will try to implement all of this type of analytic capability within a transaction database, within a highly normalized transaction database. Certainly you can do that, but you're going to run into some querying and some optimization challenges. Certainly transaction databases are optimized to get data into the tables as efficiently as possible. Well, when we talk about getting data out of the tables as efficiently as possible, and not just developers but also users doing it, well, then we need to construct a data model that's along different lines. Now, your end game here might be a couple of different forms. Some companies might build a relational data mart or data warehouse, and I'll talk about the differences here in a few minutes, according to a star schema model according to the Kimball methodology. And again, I'm a big proponent of the Ralph Kimball methodology, so I'm going to be using that here today. Now, you might also have an environment where end users want to use some of these self-service BI tools that have been talked about the last few years, like Power Pivot, Power View, for power users to get at this data. Well, certainly we have to structure it in a way where it's going to be conducive for business users, power users to get at it easily without needing to write a ton of join statements and to necessarily go ask developers constantly to write the queries to get data out. They need to have a level of independence. You might also create analytic OLAP cubes, or one of the newer methodologies that's come down the pike under the Microsoft umbrella is what we call the SSAS tabular model. Build those from the data mart for maybe more powerful advanced analytics. Now, I'm going to get into some of the physical models that you might build in just a few minutes here, but the bottom line is this is one of the early statements along the way towards building a data warehouse is the different ways that people want to look at data. Now, somewhere along the way, whether it's at the very beginning, depending upon your knowledge of the data, or maybe further on down the line, there's going to be a couple of key delivery points, a couple of flash points here. One of them is identifying all of the measure groups or fact tables, all of the business dimensions, and where they intersect. Now, coming back to here a minute, when I talked about looking at order tons, looking at production tons, looking at the tally of defects, and again, if we're in a financial environment, we might have sales over a period of time, we might have profit over a period of time, we might have returns over a period of time. Well, those might represent multiple business processes. Keep in mind, a data warehouse is not going to be just simply looking at measures that represent one business process. The data warehouse might cover many business processes. Well, each business event, each business activity might relate to a different fact table. For instance, in a manufacturing environment, we have the order process, we have the material production process, we might have the regrade or the rework process. Well, those processes happen along different time periods, and they're related to different business entities. Certainly under customer orders, you have the customer order number, but you wouldn't necessarily have customer order for other business processes. So at the end of the day, there's going to be some type of matrix for all of your business entities and all of your different business events that translate into fact tables. We'll come back into this matrix in a little while, but certainly it's important to point out that this is going to be a critical piece along the way, is identifying the matrix of where fact and dimensions come together. And sometimes they come in cleanly, and sometimes they don't come in cleanly. For instance, notice here on the left, we got the date dimension being expressed different ways. Well, a date might be a promise date for an order, or it might be a production date, it might be a defect date, so that date might serve multiple purposes. So we'll get to that shortly. Now, in a completely different type of database, one dealing with healthcare, or one simply dealing with patient visits. Well, we might have events broken out by patient flow, by patient patient count, by visits along quality indicators, and the different dimensions by which we ultimately want to slice and dice the data. So you could plug in 100 different scenarios for 100 different businesses, but at the end of the day, this is all about identifying the different business events and the measures that we want to analyze, aggregate, tally, roll up, whatever, or break down by any one of these related dimensions. So again, this is going to be an important flashpoint along the way. Now, end users, power users, think in terms of what data can we get out of the database. They're not so much interested in fact table this, fact table that, and the the direct relationships to the dimensions, although certainly they're thinking implicitly in those terms. They think in terms of how do they, what kind of information do they want to get from the data warehouse. So certainly in any data warehouse endeavor, it's extremely critical to get a good broad cross-section of the different types of reports, charts, analytics that people want to be able to produce on their own. Now, sometimes you can err on the side of focusing so much on maybe one chart or one report that you maybe develop a little bit of tunnel vision, for lack of a better word. So it's important to get a good cross-section of all the different types of analytics that are important to the high-level executives and maybe to the mid-level information workers. So certainly you're looking for both depth and breadth of information on how people want to get at data. So people might want to look at defects or regrade or rework activities over the course of time and maybe broken out by department. This is a chart that was built in one of the newer Microsoft tools called Power View, which has the ability to animate an XY scatter graph with the observations over the course of time. Well, if you're a database developer here, if you're a DBA, you're thinking in terms of, all right, what data do we need to collect? And how do we come up with a concept of a percentage? If we're going to calculate that on the fly, we need to obviously aggregate the denominator and the numerator. They're going to make up this calculation. And we need to make sure that these metrics are relatable to departments or time periods or however ways people want to look at data by. There's that magic word by again. Now, I've got several examples here. You can obviously go through the slides. I can take a look at these. But again, just to keep an eye on the different types of information that people might want to get out of a data warehouse. They might want to look at quantities of information by several different business dimensions, and maybe the ability in Excel to produce quick timeline visualizations. They once again might need to put percentages alongside of aggregated numbers. Well, as we're going to find out in a little while, it's very important to define the rules for calculation of percentages, and sometimes these are very easy, and other times they might mean some communication with the business. Maybe they've been calculating this one way for a long time, and now that you're moving to an integrated data warehouse, it might mean revisiting how some of these calculations are going to work. Now, also keep in mind when you build a data warehouse is that some people might be looking at dollars or percentages, and other people might be looking at nothing more than tallies, the number of instances where dimension members come together to form an event. So, for instance, we might have defects or regrades by a time period and by different dimensions, or if we're, let me jump forward here a few slides, if we're looking at okay, I've got another slide I'll show in a minute. We might be looking at patient counts. I'll get to that one in a minute. We might be looking at patient counts by time period and by physician or by location. So some people think that data warehouses are going to always be about dollars and cents, and that certainly may be true, but sometimes the tallies of observations can be analytically just as critical. People might want to be producing charts breaking out data by different business dimensions, so we need to make sure those relationships are in there. People might want to make multiple selections, so at any point in building relationships to fact tables, we need to make sure that people can make multiple selections of different member values. Other types of calculations we might need to put in based upon a date. For instance, we might want to look at orders or some other metric by future dates to know how many orders do we have coming up next week, or 2 weeks from now, or 3 weeks from now. Obviously, it's going to be a sliding scale because, today, obviously anything that's going on next week is going to be 1 week in the future, but next week, that's going to be week 0 or however you calculate it. So that's obviously going to have a rule for how we generate weeks future on the fly when we populate the data warehouse. Another thing that's critical in building data warehouses is knowing that not only do people want to roll up data at high levels, they want to get down to more detail levels. That's something that sometimes people tend to forget in building data warehouses, is that we're not just after the really high aggregated amounts. We want to drill down to the lowest level UPC code, product SKU, or even based upon taking a look at a pivot table in Excel here, the ability to take a number here like this count of 29 and know what were the detailed transactions that made up this 29. Was it a couple? Was it many? What were they? Well, you have the ability in some of the analytic tools like analysis services to set up what are called drill-through actions. so that someone in a tool like Excel can drill through and get all the details that made up that original number. This is a key point here in data warehousing, that the people want to be able to drill down from a high-level number to get more detailed information. So that's something that you definitely don't want to overlook. All right, well, coming back to the surface here. In order to be able to produce these at the end of the day, we're going to need to structure data in a data warehouse in fact dimension format. This is a fundamental rule in data warehousing methodology, is setting up data in fact dimension structures. The fact tables represent what happened. Typically, they're going to have the metrics that we want to roll up, like order tons or order dollars or profit dollars, whatever the measures happen to be. And then they've got foreign key pointers to the dimension tables. So the best fact tables have nothing but numbers in them, the measures that we want to roll up, and then integers that represent foreign keys that are tied to the business dimensions. So we might have a customer order dimension, we might have a date dimension, we might have a product dimension, we might have a general ledger dimension. The dimensions, loosely speaking, represent the business master tables. They provide the context to the fact data. Order tons by itself doesn't mean a whole lot unless we can break it out by the different dimension entities that we have available. Now, the process of integrating these together is what we refer to as dimension modeling. And as I get into some of the greater detail, I'm going to talk about the ways these tables tend to be related. Now, as I said, sometimes these tables can come together in a very clean and very simple way, but more often than not, you're going to have some complexities in the relationships between fact and dimension data. One of the things I'm going to talk about in a little while is a pretty common scenario in many tables, and that's what we call role-playing relationships. In other words, a dimension entity can serve multiple purposes or multiple roles in a fact table. And the most common example is a date serving as an order date, as a ship date, as a due date, and we might want to roll up dollars along the ship data line or by the time period of the delivery date versus the promise date versus whatever. So many times a single key in a dimension might serve multiple purposes in a fact table. We also have tables that might join to themselves. From time to time you'll see organizational hierarchies, people reporting to people reporting to people, or maybe units that roll up to other units that roll up to higher level units. And you've got a variable number of levels of relationships. Well, oftentimes you'll see that model with what's called a self-join relationship, where a key is tied to a parent key, and that might be tied to another parent key within the same table. And again, you usually see that for organizational hierarchy. So the whole key here is that fact tables don't always tie to dimension tables just by one relationship. There may be multiple relationships in order to be able to satisfy all the business requirements. Now, some people ask the question, how many fact tables, how many dimension tables can you have in a data warehouse? Well, there really is no practical limit. It is all about the different number of business events that you have where you're capturing data. And I'm going to use a key word here, the granularity associated with the capturing of the measure. For instance, you have a sale. Well, that sale took place on a day for a product based upon a salesman and maybe in a particular retail store. So there's your granularity. But there might be other measures that have different levels of granularity, and we'll get to them in a few minutes. But the bottom line is that every fact table represents a specific grain. So that's going to give you a guide as to how many different fact tables you might possibly have within a data warehouse. Now, we might have more advanced analytics that people want to be able to do in something like Excel. Obviously, they're going to be on their own with coming up with some of those more advanced formulas, but some people might want to plot customer sales with respect to customer counts and build an XY scatter graph in Excel and show the strength of the correlation between the two measures. So a more advanced user is going to want to do things like that. Well, that means that we obviously have to capture the sales and the customer count by, in this case, by city and over a time period so that someone can do something like this in Excel. Now, other more advanced analytic tools that people might use might be SharePoint dashboard tools like performance point services. where we might want to take a look at sales of a product over a period of time, and then sales with respect to that product's parent. So maybe we're taking a look at road bikes as a percent of bikes in general, or maybe mountain bikes as a percent of bikes in general, and bikes maybe with respect to all products. And not just for the current time period, but maybe 1 year ago. Now, a business user might sketch this out and say, I need a chart to do something like this. Well, you know that old line about a picture being worth 1,000 words, or a well-drawn picture being worth 1,000 words. Well, there might be many, maybe about 1,000, but certainly many different requirements that are going to come out of that piece of paper that someone drafts. For instance, if someone wants to take a look at the ratio of a product with respect to its parent sales, not just now, but 1 year ago, well, we need trend-based calculations, and we need to define how do we go from data for this year to data last year, and how do we account for dates being broken out by weeks or by periods. These are all things that we need to take into account. Now, again, many different companies might do it many different ways, but the point is that we need to identify what those rules are going to be. And also another thing that business users might want are KPI scorecards, especially on the corporate executive end, where they want to be able to sign on to some web dashboard or maybe open up a sheet in Excel that's been pre-populated with KPIs that represent visualizations of the company's key metrics. Well, aside from all the aesthetics of building web dashboards and building nice-looking charts and things like that, are the rules for key performance indicators. We've got KPIs here for channel revenue with respect to a goal, or internet revenue with respect to a goal. Well, obviously we need to define what those goals are and how we're going to store them in tables, and might the goals change over a period of time. Coming to the next slide here, well, we might have one rule for taking a look at a KPI for employee sales with respect to a goal, and then another rule for evaluating their percent of quota for the same time period a year ago. So, for instance, here, one of the salesmen here, Jose, his sales with respect to his quota is 80%. Well, maybe that's okay. Now, last year, his quota was 85%. So he's trending downward compared to a year ago, so that's not good. Well, again, that case statement that I just sort of verbalized here is something that needs to be identified in terms of what we're going to store in the tables. These thresholds, these goals might change over time. For instance, what is considered good and what is considered bad 1 year might change the following year. So these key performance indicators, aside from the aesthetics of making it look appealing to business users, there's still rules that are going to go on behind the scenes for these thresholds, for these goals, how they're going to be stored, and whether or not they're going to change over a period of time. The one thing you don't want to do is back yourself into a corner and set a goal that can't change. Anything can change in a data warehouse, as people who work in that environment can certainly attest. All right. Now, moving on here, I'm going to start to come up into some greater level of detail, but another point I want to make here, starting in point 2, the major components of a data warehouse. Now, I said a few minutes ago that the biggest components in a data warehouse are fact and dimension tables. Even before we get to that, and I'm going to make a little bit of a political statement here, as I get a little bit older in life, make a few political statements, and one of them is that every organization looking to build a data warehouse that represents the flow of data, that represents their business process, needs to have something along the lines of a scenario diagram, a storyboard. Now, it's more important that you do it as opposed to what tool you do it in. You can do it in Visio, you can do it in Word, you can do it in PowerPoint for that matter. It's more important that you have something, because any scenario drawn out like this is going to tell a story of what some of the data requirements are going to be. For instance, I worked in consumer packaged goods for a number of years, and consumer packaged goods is a great example of some of the challenges you have in data warehousing. There might be an internal database for order entry and demand management and invoicing and things like that, and that data might be captured in SQL Server or in Oracle or Power Builder or whatever the internal database is, and that data is captured, the invoice number, the date, the ship account, the product SKU. That might be the level of granularity of the data that's stored at the internal level in the operational system, but that doesn't represent the whole picture. You might have region managers who are setting budget quotas and forecasting numbers. They might be setting up operational plans, what they're looking to ship, what they're looking to to have in revenue, what the projected profit, what the target profit is going to be, and maybe that's at a higher grade. You certainly aren't going to set budgets down at the product SKU level, not normally. You're going to set them maybe one level up at a brand, and maybe by month or quarter and by region. And maybe they transmit those in by FTP or by some other process. And maybe they budget in cases, whereas internally we deal in our order management system in pounds. And then we have cost of goods feeds, maybe because some of our product is manufactured by outside processors, and so they provide a cost of goods feed that's maybe by product group and by month. Well, you probably see where I'm going with this. We got different metrics here being provided at different levels of granularity, but it gets a whole lot worse. We might have sales brokers or field salespeople who are selling the product or working with the retailer to promote the product, and maybe they build promotion plans to push the product out in the retail area by market and by time period. They might set up special events to run throughout the course of a year and run discounts at different time periods, and they deal with things like the bill account and the product SKU and a time period and an event type that might be tied to a general ledger code. Now, a little side note here. It's almost inevitable that some of the data in data warehouse might wind up tying to a GL system. Now, that's a topic for another day. You can obviously go 100 different ways, 100 different directions with that, but the bottom line is that some of the data in a data warehouse might tie to data in a GL system. So very likely you're going to have some GL entities in here. Maybe if it's just simply expense accounts, general ledger codes, or whatever. Well, continuing this process, the manufacturer might ship the product not directly to the stores, but maybe to distribution centers, and those distribution centers turn around and push it into the retailer area. Well, the retailer doesn't deal with pounds. They might deal with consumer units, and they might deal with UPC codes. And well, the manufacturer ultimately wants to be able to look at the big picture, but they've got to get that retail data back from syndicated suppliers who are more than happy to provide that data for a rather large cost, but the manufacturer has no choice. They want the data, and so they're going to have a data feed coming back, and that's at a different level of granularity. So right at the start, we need to deal with conversion factors going forward from pounds to cases, cases to units, mapping tables to go from one product code format to another, relationship tables between ship account, bill account, and being able to deal with data at different levels of granularity, what will roll up and what won't roll up. So any person who's been in data warehousing knows that you're going to spend several days, several weeks, maybe even longer, whiteboarding all of the different requirements that come out of this. So everyone should have this. A challenge I run into sometimes as a consultant over the years with different clients is getting them to produce something like this, because it's in their heads, and so they figure if it's in their heads, why is it necessary to go through the time to put it out on the whiteboard? Well, you can see requirements, data requirements, requirements for relationships that never occurred to you until you go through this process. So I can't emphasize enough how important it is to build a storyboard. Well, along with that is some kind of topology diagram that represents what's the picture going to be of data coming from the original sources all the way to our data mart or whatever the end game is going to be. So we might have 3 or 4 external sources, and our end game is for business users to be able to roll up, to slice and dice, to be able to do their reporting against the data that's in these different sources. Now, some people might say, well, if these sources are in a transaction database, why can't the users go against the transaction database? Well, they could, but you're going to run into all sorts of challenges in doing so. Really, the recommended approach is to build some kind of data warehouse or data mart to store that information. And then possibly, if you want to have some more advanced analytics, build an OLAP cube. Now, here's the thing. You can walk into 10 different companies and see 7 different variations of this. Some people might not build OLAP cubes. They might just simply build a denormalized data warehouse, or a data warehouse that further breaks down into individual data marts that cover different business processes. There's no one rule that says how this should be structured. There could be a variety of factors, and maybe even the learning curve that you're willing to go through to maybe learn OLAP on whether or not you want to build OLAP cubes. So the point is to build one that's going to be tailored towards a particular organization. Now, another example of a topology that might get into more specifics, might get into different servers, maybe requirements for how often data marts are going to be populated. So we might read from 3 different sources and populate a production server daily at a certain time, and then turn around and populate either a staging area or a data mart or a data warehouse maybe 1 hour later, and then make that data available in the form of views or an OLAP cube or whatever to end users to be able to get at the data. Now, depending upon the type of environment you're in, maybe the ability to rebuild everything overnight and the users are working with data that is 1 day old, maybe that's good enough. But in other environments, that's not going to cut it. Maybe these business users need to get at data that's made its way into the transaction database 5 minutes ago. So you've got much more aggressive incremental updates. Now, I'm not going to get into how you would populate those, the different SQL techniques. That's a topic for another day. But the point is that you're going to have to come up with the rules for what the latency is, whether the latency can be 1 day, half a day, 1 hour, or in the case of somebody like the Chicago Transit Authority looking at transportation schedules, they need to have data that's obviously very, very up to date. So that latency is something that needs to be defined and needs to be understood with the business. There may be some limitations that you're dealing with, either in terms of hardware or in the schedule of the data, that might mean that users are only going to see data that's 1 hour old, 4 hours old. This is an important thing to identify, is the latency of every stage of the data. All right, now as I said, the structure, the physical structure of a data warehouse is going to be facts and dimension tables. Now, these can be physical tables. So we might have a table called fact resellers that's read from the transaction data that has the necessary measures like sales amount and tax amount and freight and product cost, broken out by the different business dimensions, like date for order date, due date, and ship date, by reseller, so we can look at sales by reseller or by the related product line or the related business type, and so on and so on. Now, these could also be views. Something that's become rather popular over time is to abstract fact and dimension tables from views. So you might never actually see a table in a data warehouse called fact reseller sales. It might be a view that's read from other tables. Now, there are going to be some pros and cons to doing that based upon performance, based upon how frequently that data gets updated. So there's no one size fits all, but the bottom line is, at the end of the day, we need to have a structure that's along these lines as the starting point for constructing a data warehouse. Again, the ideal fact tables are going to have nothing but numbers in them. Integer keys for the foreign keys that tie to the business dimensions, and then either integers for quantities, or maybe currency columns or decimal columns to hold things like tax amount and sales amount, depending upon the precision of the data. Now, for people coming from transaction environments, this is kind of a culture shock because they're used to normalizing data. I know when I first got into data warehousing, my thought was, why are you denormalizing everything? Why is it that in dim product here that we have the product along with the subcategory and the category? Shouldn't they be separate tables? Well, again, we have to remember why we normalize. We normalize to get data into tables as efficiently as possible. Data warehousing is about getting data out of tables and into the hands of users as efficiently as possible. And in that sense, a more denormalized, a more flattened structure is going to be much more conducive for reporting. Now, a while ago, I had a matrix of fact tables and dimensions, and I'm going to basically talk about the same thing here, but from a little different perspective. One of the things that's discussed in the Kibble methodology is what's referred to as a bus architecture, or some people would say the dimension usage matrix. Now, we might start out at a very high level. We might have a retail sales process, and we might have the process of setting goals, and we might have a warehouse inventory process, and we might have a purchase order process. Now, each one of these processes might spawn one fact table or might spawn multiple fact tables. So this might be a precursor before we actually identify the fact tables to identify what the business processes are. and then the primary business entities by which we want to look at the data. Now, there's not going to be too many cases where every business dimension is going to be tied to every fact table. We're going to have gaps in here. For instance, the promotion dimension for the different promotions we offer only makes sense for retail sales. Promotion has no bearing on the warehouse process. So these NAs aren't bad things, they just represent the dead zones here. We don't break out warehouse inventory by promotion because that wouldn't make any sense. So there are going to be gaps, but there will certainly be common dimensions. Certainly data is going to be a common dimension for most fact tables. Product is another one. So it's important to identify this kind of a matrix. Now again, for some people this might seem like pretty elementary, almost pedestrian or pedantic type activities. They're still important, if nothing more than for self-documentation purposes. So again, at the risk of repetition, the Data Warehouse Toolkit by Ralph Kimball covers a lot of these concepts in great detail. Just to talk about the book for a minute, what the Data Warehouse Toolkit does in the book, it actually goes through different business scenarios, different industries. Like there's a chapter for retail industry, and there's a chapter for the insurance industry, and there's a chapter for the telecommunications industry, and the different fact dimension relationship challenges that you might run into. But one of the things I can't stress enough is to shape your data from the transaction system or from your source data into star schema fact dimension tables using surrogate keys. There are many different benefits to doing so. As a matter of fact, for people who remember TV from the 70s, there used to be that famous H&R Block commercial they had on TV. The commercial went along the lines of the 50 reasons why you should have H&R Block do your taxes, or whatever the commercial was. Well, you almost have a commercial today about the X number of reasons why you should structure your data in fact dimension tables using surrogate integer keys. One of which is the fact that you can take maximum advantage of some of the newer capabilities that are in SQL Server. The column store index used in the X-Velocity engine under the hood. The column store index is going to work best against fact tables that are built using surrogate integer keys. That's again a topic for another day, but definitely recommend you take a look at column store indexes if you're building SQL Server data warehouses with SQL 2012 and beyond. All right, now I mentioned the bus matrix a minute ago. This is just simply another look at it. And if you wonder why they call it a bus matrix for the relationship between the business events and the dimension tables, it's almost like the seats on a bus. Some of the seats are going to be open, some of the seats are going to be closed where you have the intersection points. So again, these are milestones along the way. They might seem very, very fundamental, but they're critical towards building the necessary definitions for a data warehouse. All right, now we're going to start looking at the types of fact tables. We're going to start getting into greater levels of detail. And there are three general types of fact tables, and here we go. First of all, the most common type of fact table is what we refer to as a cumulative transactional fact table. Now, the reason we call it the reason that we call it a cumulative transaction fact table, and the reason we have different names for different types of them, are because of the way we populate them and also the way we read data out of them. Now, this is the most common type of fact table. These represent transactions that occur throughout the course of a day, a week, or maybe even every 5 minutes or every 5 seconds or every 5 milliseconds if you're maybe dealing with an application on Wall Street. So over here on the left, I've got two different examples, fact sales and fact budget. So fact sales, we might have sales every day by customer, by product, where we're tracking the dollars sold and the units sold. And we might have other dimension entities as well, but at a minimum, we would have these. Now, in a cumulative transactional fact table, the measures here are what we call fully aggregatable. They can be rolled up by any or all of the related dimensions. So for dollars sold and for units sold, I can roll up those numbers by anything associated with the date dimension, like date, month, year, quarter, whatever, by anything in the customer dimension, customer, customer region, customer market, and by anything in the product dimension. There's no limit as to how I can aggregate data. As I said a while ago, every fact table has to have an understood grain statement, the level of detail. Well, here it's the date, the customer, and the product. That's an oversimplified one, but you get the point. Now, transactional fact tables don't necessarily have to be down at a very low grain. For instance, we might have a budget process where we come up with what we're budgeting to spend and what we're budgeting to ship, or what our budgeted volume is going to be, and that date might represent the first day of every quarter. So maybe we budget by quarter, and maybe for a product group, and maybe for a geography region. Now, this is obviously at a much higher grain than fact sales, but that's okay. It's a different fact table because we have a different grain statement, and there's no rules for how, or no restrictions for how we can aggregate data. We can aggregate it by any or all of the related dimensions. Now, obviously, I can't aggregate budgeted spend by product SKU because product SKU is lower than product group. So there's one implication here that we can only aggregate these numbers based upon the dimension entities or anything higher within that dimension. And again, as I said, these tables really operate best if we have nothing but numeric data in them. Integer surrogate keys for the foreign keys, and then either integers or decimal columns or numeric columns or whatever for the measures. So that's cumulative transactional fact tables. Now, one other thing before I move on. With the data warehouse, the idea is that the data that you're pumping into it, either every 5 minutes or every day or every week or every hour, however often you're populating the data, the idea is that the data there is correct, that it's been cleaned, that it's been scrubbed, that it's correct. Well, no situation, no organization is perfect. Maybe we pump data into a fact table and we realize we've got to make some corrections. Well, corrections might be a problem because that data that's in the data warehouse might have been used to pass on to other systems, or maybe to an OLAP queue. So simply issuing a correction, issuing an update, that might not be possible or might not be practical. In that case, what might possibly happen, especially in an accounting environment, is you might send in reversing entries. So let's say that you had a sale for a product, it was $100, but it was supposed to be $120. Well, it's very possible that the correction might take the form of 2 rows. A row with the same foreign keys but with reversing numbers for the dollars sold, and then the correct row coming in. Now, any analytic tool is going to roll it up to the correct number. So that's something to keep in mind when dealing with corrections, is that it might not be possible to update the data. You might actually have to issue a correcting record and then the valid record. It actually happens more times than you might necessarily realize. All right, now there's a variation of a transactional fact table, and it's what we call a factless fact table. Almost sounds like a contradiction in terms. A factless fact table has no measures per se. Now that doesn't sound all that interesting, but depending upon the type of analytics that are done, it might be very critical. We're looking at tallies, we're looking at counts. So for instance, if we have a data mart table or data warehouse table for people signing up for a class in a university or a technical school or whatever, well, we might have a fact table that tracks the date, the course, the sales rep, and the applicant, but there are no measures in here. What we're looking to capture is the number of times when these dimensions come together to form an event, in this case the enrollment of a person. Now sometimes you might have an integer in here with a value of a 1 or a 0. Some people might use a small int or an int where the value stored might be 1, 0, or possibly -1, and they might sum up that number. So a factless fact table might not have any measures in it, or it might have a single measure with the value of 1, 0, -1 stored. It can be done either way. And that again is used for tallies that we might look at by course and by time period and by sales rep in order to see if somebody's tally of people signed up is either going up or going down. So it can still be very, very critical from an analytics standpoint. And an example of a factless fact table here is maybe looking at the number of visits from a medical application by year, by physician group, and broken out by gender. So this might be a factless fact table that had the date, the physician foreign key, the visit type, and the gender, and that's it. And so we can produce something like that in Excel or from a report reading from that table. So factless fact tables can be very critical for applications. So again, it might not be anything other than a fact table with the foreign keys tied to the different business dimensions that represent the different dimension entities by which we might want to look at the roll-up of the count. All right, then we have what are called periodic snapshot fact tables. These you'll see from time to time. Not every data warehouse is going to have them, but virtually every data warehouse will have the transactional fact tables we looked at. Some of them might have what we call snapshot fact tables. Now, the best example of a snapshot fact table, probably everyone here has a bank account. Well, you probably get a statement from your bank at the end of the month or end of the banking period, and it might have your beginning balance at the beginning of the period and your ending balance. Well, you get a statement every month. Well, you wouldn't look at all 12 of those statements and add up your beginning balance and your ending balance because the number wouldn't make any sense. You might take an average of it, or you might look at just 1 month, but you wouldn't aggregate it across all the different related dimensions because the number wouldn't have any analytic value. That's the concept of a snapshot fact table. A snapshot fact table is taking a picture, a point in time measure of a balance or some kind of a value. So we might have a fact table of account balances by customer, by account, by the date that might be the first day or the last day of the month, the starting and the ending balance. And maybe we might average those balances over the course of time. Maybe we might sum the starting balance for everybody but just for 1 month. So these numbers are not fully additive. They're what we call semi-additive or semi-aggregatable. That's the nature of a snapshot fact table. Another example down here at the bottom is inventory balances. You might take inventory once a month. Well, the quantity on hand for one product might be 10, and then the next month you take inventory and the quantity on hand for another product might be 8. Well, you wouldn't add those two numbers together. That wouldn't make much sense. You might take an average of it, but you wouldn't sum the numbers. Because again, those numbers didn't represent transactions along the way. They represented a snapshot of what things looked like at a particular point in time. Resident counts within a healthcare program. I used to work in the what's called WIC, the Women, Infants, and Children program, many years ago. Well, we took snapshots of the number of adults, infants, and children on the program at the end of a month. We might use that to produce averages, but we certainly wouldn't sum them by every county, by every date, because the same person might be counted for 5 months in a row. Well, that obviously wouldn't make any sense. So that's another example of what we call a snapshot fact table, where we're taking a picture of what data looked like. Now, there might be special ETL processes to populate these tables. We might, at the end of the month, read from the transactions to produce these balances or to produce these tallies. And they might be used for reporting purposes, but again, there are going to be rules about how we can aggregate the data. Now, there is a variation. I actually only put this in the slide recently because the last time I did this presentation, someone asked this question. There is a variation of snapshot fact tables, and it's called accumulating snapshot fact tables. These are rather unusual. The most common example is, let's say you have a mortgage fact table, where a single row doesn't get populated and completed in one insert statement. It might take several phases, several business processes before the row is completed. So you might have an entry in a fact table where an initial dollar amount is approved by a mortgage manager, but then there's going to be a certain amount that's approved by underwriting, and then maybe the final approval, and that process might take weeks or months. And maybe those are separate columns in the fact table. So we call that an accumulating snapshot fact table because data is accumulating in the row over a course of time. So edits to the rows are commonplace. Again, that's not a common one, but I've just mentioned it here for completeness. So those are the types of fact tables that we see in a data warehouse. Now, as far as dimensions go, the dimensions, again, loosely speaking, represent the different business master tables that provide context to the fact data. Now, most data warehouses are going to have things like a product dimension, or if you don't offer products, maybe you offer services. So you might have a service dimension. Now, you also probably have customers or patients or people whom you deal with, you provide services for, an account dimension, however you're going to call it. You're typically going to have one of those. And I have yet to see a data warehouse that didn't have a date dimension because most people want to look at data by date. Now, there's certain pieces of information that you're typically going to see in most dimensions, if not all. First of all, most, I dare say close to all dimensions are going to have an identity column. A 4-byte integer or maybe an 8-byte integer if you have a huge number of entries in that dimension that represents the surrogate primary key for that table. So we might have a product PK, a customer PK, and a date PK that's generated by the system. In the case of SQL Server, an identity column. Well, then we might have a business key that we use for ETL purposes when we read in data from the source system. So we might have a product SKU here, a customer number, and an actual date. And you might possibly have a constraint that that value is unique within the table. Not always, but maybe. And then one or more description columns. You might have a short description and a long description for different reporting requirements. And then the different attributes that further describe that business entity. So we might have 25,000 products and 50,000 customers, and we might have one row and a date dimension for every day of the year for 5 years. Well, we got attributes that describe every row. In the case of products, we might have a subgroup, a group, and a brand, and maybe those roll up. So we might define in an analytic tool that product SKUs roll up to subgroups, which roll up to groups, which roll up to brands. And in the case of a customer dimension, we might have markets that roll up to regions, roll up to zones, and we might have multiple hierarchies. For instance, Kroger in Atlanta might belong to Atlanta, which is part of the state of Georgia, which is part of the southeast region, which is part of the eastern zone of the United States, but it also might roll up to a corporate grouping of Kroger, and maybe Kroger is owned by another division which owns another corporate group. So we might have multiple hierarchies in here that don't necessarily have anything to do with each other, but it represents the different ways that people want to roll up data. Now, not all attributes in here are going to have parent-child relationships. For instance, a product's color and a product's size and a product's weight might not necessarily have anything to do with each other. So they're basically free-form attributes. You wouldn't drill down from color to size because maybe there's no relationship there. Now, the other thing to bring up, and this is a key thing that you'll find when you start to build business dimensions, we might have 25,000 products, and maybe if we did a select distinct of each weight, we might have 20,000 different weights. Well, you may or you may not want to store the weight exactly in that form. It depends upon the type of analytics you want to do. If someone wants to look at sales by product weight, and they go in Excel and they produce some type of a pivot table and they break out sales by weight, and you've got 20,000 different unique weights, well, that's not going to be a very helpful pivot table, but not likely. So what you might do is you might go through a process, I'm going to use a nice 50-cent term here, called discretization, where we might summarize those weights maybe by ranges. So maybe anything from 1 ounce up to 8 ounces we might have in a range, and that might cover hundreds of rows. So instead of having 20,000 unique weights, maybe you have a much more manageable set of weights. Again, that's going to be driven largely by the business. If you're dealing maybe with fine metals or something like that, maybe the weight down to the ounce or maybe even beyond, maybe that's critical, and you can't build a more discrete range of values. Again, the business is going to decide it. Now, one other thing here, and I'm going to talk specifically about the date dimension. Again, no two clients are going to look at dates exactly the same way. Some people might have very, very basic rules for aggregating based upon time period. They will look at data by, yeah.
Hey, Kevin, it is over an hour right now, so I didn't know how much longer you have for the presentation.
I'll tell you what, I can probably finish, yeah, I just now looked at the clock and realized it was 1 o'clock. I can probably finish this in about 15 minutes if that's okay, if I can have another 15 minutes to get through it.
Yeah, that's fine. We'll continue. For those who can stay on, please stay with us. And if not, this is being recorded and will be posted on the website, and we'll do the questions at the end.
Okay, thanks. So some companies might look at sales by month and by quarter and by year, and that's it. So their date definitions are very, very basic. Others might be a little bit more complicated. They might have one calendar that's based upon the actual date calendar, and then they might have another date requirement by fiscal definition, which might run from October to the following September, or maybe from July to the following June. So we might have multiple attributes in here to describe the date. And then it might even get more complicated. Maybe you're in an environment where we need to deal with what's called seasonality, where we need to look at sales across years, but where the dates aren't exactly the same. And the first time I ever dealt with seasonality was probably one of the more complicated examples you'll find. I work with a company that on a sales application that was responsible for making Mrs. Paul's fish sticks. Well, if you know anything about this particular topic, you know that during the period of Lent and the weeks before Easter, sales of fish products are going to be very high. And so they were interested in knowing the trend of sales for the first Lent week versus the second Lent week versus the third Lent week across years. Well, since Easter is a different time period every year, the first Lent week in one year might be sometime in February, and another time it might be later in February or early in March, or however the dates happen to shake out. So we might store in a date dimension a marker for what Lent week a particular date represents so that we can line up the sales by Lent week across years. That's a more complicated example, but the point is that if you have dates that vary over time, like the traditional shopping day after Friday, after Thanksgiving, which most people call Black Friday, that might be a different date every year, so we might have a flag in there. And then to make matters even more complicated, we might have a time dimension, because maybe we want to look at sales not just by date but also by time. And maybe not necessarily down to the minute, maybe in 15-minute intervals. So we might have a separate time dimension with all the different intervals throughout the day and an AM PM indicator and a primary key here that we might store as a foreign key in the fact table. Again, the chronological requirements for reporting are going to dictate what we have in a date dimension. Now, dimensions, as a general rule, you want to build them as flat, denormalized star schema structures. So back here, we wouldn't have a separate dim product group and dim product brand. We flatten them into one business dimension. It makes reporting easier. It makes, if we want to track multiple versions of our product over time because maybe the color or the weight changes, it makes it a lot easier if they're flattened in one table. Now, once in a great while, you might see an exception to that where people build a business dimension out over multiple tables. We call that a snowflake schema. They're not horrible, they're not the end of the world, but they can introduce some complications. So it's only when you have an exception that you want to build them, and that's in what we call a dimension outrigger, which I'm going to talk about in just a minute here. Now, moving on here, another type of relationship, and I spoke to this earlier, is what we call a role-playing relationship, where a date can serve multiple roles. Most common example is dates, but it can be any dimension. So a date might serve three different purposes in a fact table: the order date, the due date, and the ship date, so that we can roll up order dollars by any of those date definitions. I've had clients that have had up to 6 roles for a date. They had a production date, a work in progress date, a ship date, a delivery date, due date. So obviously role-playing dimensions can be very, very important for clients. And the key is just to identify what different roles that dimension is going to play. Now, if you're curious about an example other than dates, a good example might be an airline dimension. You might be scheduled to land in one airport, but maybe you have a flight problem. You wind up landing in another airport. So in a fact table of flight arrivals, you might have the intended destination airport code and then the actual airport code for those few times where you might, you're scheduled to land in Atlanta, and next thing you know, you're landing in Orlando because of some major storm or whatever. So that's another example of a role-playing dimension. Now, one thing I do want to mention here, try not to get too much involved in some of the more recent tools that Microsoft provides, but if you're working in something like analysis services in the tabular model, unlike some of the other analytic tools that Microsoft provides, where the role-playing relationship is directly supported in the tool, something like SSAS Tabular doesn't have direct support for role-playing dimensions. You've got to either build 3 views of that date dimension, or you've got to extend the model with some DAX formulas to have, say, sum of ship sales amount based upon one relationship, sum of due date amount based upon another relationship. You're going to have to build a few additional items. Now, analysis services handles it natively. In the dimension fact table matrix, if it senses multiple relationships, it'll build multiple views of that dimension automatically. So if you have an account that could serve as an invoice account or a purchase order account, or if you have a date that could serve as an invoice date or a pay date or a due date, The full-blown analysis services OLAP tool will handle that automatically. All right, another topic that we might run into. There are some times where we might have dimensions that aren't necessarily that deep in terms of the number of attributes, but we have several of them. For instance, we might have orders based upon order type, order status, order payment, order category, order this, order that. And maybe all we have is a description. Maybe there aren't any other identifiers for it other than description, but we want people to be able to roll up orders by those different entities. Well, does that mean that we have to have a dimension for this and this and this and this, even though we've only got a handful of rows? Well, you can do that, but here's another pattern you can use. It's what's called a junk dimension. Now, it has kind of a negative connotation, but it's actually pretty helpful. What you can do instead is basically flatten these using a cross join, or basically you're creating a Cartesian product with a SQL statement to do a cross join of all of these into one flat table. So you've got every combination of type, status, order payment type, order category, whatever, and then a single primary key that represents each combination. And then you store that in the fact table. So if you want to sum up sales amount by specific order types or statuses, you can still do so. Now, this isn't a fantastic pattern. You can certainly do it the way over here on the left, but you usually find that the pattern over here on the right of creating one junk dimension is going to be easier. So if you have multiple dimensions that are like this, instead of creating this kind of effect of one dimension for each one of these small entities, just do a cross join and create a Cartesian product of all of the other values sort of flat together into one table. All right, now I mentioned a minute ago that for the most part we want to create flat denormalized dimensions. There's one exception to that, and it's what we call a dimension outrigger. Here's an example where we might break a dimension into multiple pieces. And this is actually directly from the Ralph Kimball book. Let's say that we have hundreds of thousands of customers, and they all belong to specific counties. And those counties themselves have attributes tied not to the customer, but to the county. So for instance, of the X number of thousand customers, we might have 100 counties. And each county has specific attributes for population under 5 years, percent that's female, percent that's male, and so on. Well, if you follow the rule of one flat table to the extreme, you have a high number of values that wouldn't necessarily vary that much by individual customer. So when we have this what we call a low cardinality attribute situation where these aren't going to vary much by customer, but by county, we might store just the county in the customer dimension and have a separate what we call outrigger dimension with attributes specific to the parent county. So when you have that kind of pattern, you create what's called a dimension outrigger. This is not a terribly common pattern, but it's to avoid having one big fat dimension. All right, now this last one here, or excuse me, point 10 here, I'm going to go over this very, very quickly because I want to get the last couple of points. Many-to-many bridge relationships. You could spend an entire day talking about these. They are the most complicated type of relationship in a data warehouse, but they're ones that you will come up with from time to time. It's important to understand the pattern here. For instance, let's say that we are looking at sales of books that are written by authors. Well, if you know anything about computer books or any type of book, you know that a book might be written by multiple authors. And an author might be responsible for writing multiple books. Well, the sales is based upon the book, not based upon the author's name because there could be multiple authors. Well, those authors might have an author share. An author on one book might write such a percent, and another author might write such a percent. So in order for us to be able to take a look at sales by author and factor in the author's share for purposes of royalty, we might need a bridge table that joins the book dimension directly and one other dimension, in this case the author, that's not tied to the original sales table. So the relationship between sales and authors is going to be through the bridge table. Now that sounds kind of complicated except when you start looking at other scenarios. For instance, a currency situation where currency can vary. We might have currencies for different countries where the average rate varies by day. Well, we might store the sales by the United States dollar, but we might want to be able to equate sales for other days by different currencies. Well, we would need a bridge table that holds the date, the currency, and the average rate or the end of the day rate depending upon the accounting method. So we got the same pattern here. And then finally, if we're taking a look at shipments of a product initially by the lowest unit of measure like pound, but we want to be able to express the shipments in terms of other units of measure like cases or retail units. We might have a conversion rate table that stores every product or product group, the unit of measure, and the conversion rate, so that if we want to express shipments by unit of measure, even though we only ever store pounds, we can bounce off that bridge table because that bridge table has one other dimension in common. Now, I've got some notes here in the slide deck that you can take a look at. This is something that, again, is the probably the most complicated type of relationship, but it's one that you do want to be aware of because it can happen with data warehouses. Now, I'm going to jump ahead just a little bit because item 11 here, type 2 slowly change dimensions. I'm not going to have time to talk about that, and I want to get to the last 2 points here. Bottom line is type 2 change dimensions represent dimensions that change over time, and we want to track the history associated with a change. So let's say that a book or any product is $49.95 for years, but that its price goes up to $54.95. Well, we want to track sales under the old price as well as the new price. Well, basically the pattern is in the dimension to store revisions of that book ISBN number according to a date range and the price, and then write out the necessary PK to the fact table based upon the date of that sale. So if a sale takes place after the prices change, you write out the second book PK into the fact table. That's going to allow you to take a look at sales and returns when the book was under one price versus another. Now, there's some considerations that you need to take into account with early and late arriving data and handling of the start and end dates. I've got some notes in the slide deck. Actually, I have a number of notes in the slide deck that you can take a look at. This is something that Kimball actually devotes quite a bit of time to in the book. This is something, if you work in data warehousing, you definitely want to understand the pattern here, because this can be a key aspect of many data warehouses, is the ability to take a look at a dimension entity that changes slowly over time, and a product whose price changes, and be able to look at the trend of sales both before and after the price change can be critical. All right, last 2 items here very, very quickly. Two big no-nos. One of them is storing null values in a fact table for foreign keys. In a word, don't do it. Here's an example. Suppose you have a fact table with sales measures, and you have a product key and a geography key, and you also have a cost center key that relates to a cost center master. But let's say that for 5% of the sales, there is no cost center. Well, you might think, okay, you store a null in there. Well, here's the problem. Users might want to aggregate the sales for the other cost centers and compare it to the sales where there was no cost center. If we instead store some special value in the cost center master, like an NA or an unclassified cost center, maybe with a special foreign key, or a special primary key that we would use as a foreign key, like a -1 or a -999 or some value like that. So instead of storing a null, we store that special value. That's going to allow users to aggregate by the valid cost centers and also see the sales where there was an unused cost center. Ralph Kimball talks about this pattern in his book. Definitely recommend using that and not storing null values in fact tables for foreign keys. It's going to give your users more capabilities. And then finally, another big no-no, and I see this happen from time to time, it's storing ratios in fact tables, but basically storing calculations that result from division. In a word, you don't want to do it. And here's the simplest example. Let's say that we have a calculation of return rate, the return dollars divided by total revenue. Let's say we have 2 stores. Well, store A has $10 in returns and $20 in sales. Well, you might think, okay, we store the return rate in the fact table of 0.5 or 50%. And then store B, we have $10 in returns but $100 in sales. So the return rate there is 10%. Well, you probably see where I'm going with this. You wouldn't aggregate the 50 and the 10 because there is no analytic meaning to it. We would want to get a weighted average. So we would sum up the number that represents the numerator and the denominator and have a calculation on the fly. So the bottom line is you typically don't want to store measures that represent percentages or ratios that are derived from division because they don't aggregate in any kind of a sensible manner. So the best practice is to store the numbers that represent the numerator and denominator and have a calculation on the fly. So, lot here to cover. Thanks. I noticed the attendees is still almost the same as when we started, so appreciate everybody hanging around. At the end of the slide deck here, including the Ralph Kimball book that I mentioned at the beginning, if you want to get more involved in building analysis services, tablet projects, a book by Chris Webber, Alberto Ferrari, and Marco Russo on the tabular model. And also, if you build analytic cubes, the same authors, Chris Webb, Alberto Ferrari, and Marco Russo, have a fantastic book on building analysis services cubes with SQL Server 2008. So I highly recommend both of these books in addition to the Ralph Kimball book. So thanks everybody for hanging around, and
yeah, we'll take
questions
in a few minutes. I just wanted to mention that Safa Hariton has won the raffle for today. Mm-hmm. And then I'll just get with the questions here. Is there different types of data warehouses? If so, that also implies there's different types of modeling per data warehouse type. For example, what is the real-time DW? What is the top-down, the down-up? And do these types require different modeling types?
Yeah, they're going to require, to give a brief answer, they're definitely going to require different types of approaches, both with the populating of the data as well as the way the data is modeled. Now, as far as the top-down versus the bottom-up, or as some people would say, the Ralph Kimball methodology versus the Bill Inman methodology. Let me come back to one of my early slides here, where I had some of the high-level topology. Some people might initially construct a data warehouse that represents the entire picture of the company and then spawn data marts off of that. Other companies might take the opposite approach, and actually what I'm about to describe is maybe a little bit more common. Some companies will build individual data marts that represent different business processes, different segments of the company, and then roll them up to one unified data warehouse. Now, some of that is actually going to be predicated, and this is going to sound like a kind of a controversial answer, but some of that might be predicated on how the project initially started. It might seem like not very purist to say, and certainly you want to take as pure an approach in building data warehouse as possible, but sometimes an organization might start building along one path and realize, you know what, we really should have taken the opposite approach. They might start building a data warehouse and figure they would spawn data marts off of it, and realize a year into the project, you know what, we should have done the reverse. Well, unfortunately, if you've got a certain amount of work that's been expensed along a certain path, you might have to continue with that path, even though you might not necessarily view it as ideal. It'd be great to say that every data warehouse out there is ideal and is the way everybody envisioned it from the get-go, but it just doesn't always happen that way. So some are actually built from the top down, and some are built from the bottom up. Some are more normalized than others, or some are more denormalized than others. So how much somebody might be, or a data warehouse might be impacted by the Kimball methodology of usually denormalizing data might depend upon the vision of the original data architects on the team. Now, as far as the whole real-time concept, that is a topic that could definitely spawn an entire conversation, because we get into issues of, the minute the data hits a particular data mart or a particular transaction database, is the ability for end users to be able to get to it. Now, that's been a challenge. That's been a huge challenge over the last several years, partly because of the technology, partly because of maybe system requirements. Well, Microsoft, I'm going to focus on them because that's the vendor I work with, it's the platform I work with the most. Microsoft has made some pretty significant strides over the last couple of years towards making real-time access in a data warehousing scenario more of a possibility. They've introduced a platform known as Parallel Data Warehouse. It's actually an appliance. It's a combination of hardware and an optimized version of SQL Server that scales out much further than even the enterprise version of SQL Server does. And it allows you to implement basically real-time access to data. Let's say you might build an analytic cube, but you still want real-time access to the data using the rollout methodology. Well, there are hooks in place to be able to do that without necessarily sacrificing performance. So that's been the whole idea of real-time access to data has been a real challenge over the years because of the different limitations either with the technology or with the hardware, and you're seeing offerings, by Oracle and by Microsoft with Parallel Data Warehouse to try to make some of those things a reality. If you work in the Microsoft environment, I would definitely take a look at Parallel Data Warehouse, and also a shout out to Pragmatic Works, because Pragmatic Works has actually produced a lot of white papers based upon case studies of applications they've done with Parallel Data Warehouse. So if you want to see how some people are actually implementing it, I would take a look at that.
Okay, the next question is, how would I bring in status flow data into a fact dimension model, and would I have to create a fact for each status, or is there another recipe to do this when I would like to analyze status flows?
Okay, tell you what, if you can get the name of that person, because I'd like to explore that one a little bit more in detail. Basically, as far as what kind of data he means by status flows. Typically, every row in a fact table represents a transaction or an event or something that happened. So to use an analogy, in a retail environment, if you have 100 sales in the course of a day, you probably have 100 rows in the fact table, or maybe 120 if maybe the sales were for if you had multiple products in some of the transactions. So typically every row in a fact table represents something that happened and a metric along with it. Now, as far as the status flows, I need to know what kind of status flows we're talking about here. So if you can grab that person's name, and maybe I can explore that one a little bit further.
I will send you a list of all the questions at the end, all that information.
Sure.
Unfortunately, the next one was, while on this slide, could you touch on the SCD, the slowly changing dimension, in loading a data warehouse?
Yeah, let me come back to that slide deck. Slowly changing dimensions are just like a lot of topics here, but definitely this one can occupy an entire day's worth of a conversation. The challenges of all the slowly change dimension with loading it are, first of all, capturing the nature of the change. So if you have a book whose price has changed from $49.95 to $54.95, or a product that used to be marketed under one market segment and now it's marketed under another market segment, and you want to capture history associated with the change, the first thing is to capture the change itself. Now, that change might occur in a transaction system, so you might use audit trail triggers, or you might use change data capture or some other methodology in your transaction system to capture the change. But the first order of business is to capture that change and get that into the data warehouse as quickly as possible. Because the last thing you want to do is, let's say that today is what, April the 22nd, whatever day today is in April. Let's say that a product's price changed, but you're just now getting it today. But it changed back on April the 1st. Well, that means that you've been posting sales to your sales transaction ledger, or your sales transaction table, based upon your belief that the product was still under the original price, when in fact it changed earlier in the month. You're getting late arriving data. And late arriving data can be a bit of a pain in a slowly change dimension environment, because you might have to go cancel out or issue reversing entries on all those products based upon the wrong foreign key, because you want them now to have the new foreign key based upon the product with the new price. So getting the changes in sync and knowing that you've got a process that gets those changes to you as quickly as possible is half the battle. Now, as far as the population of it and retiring the old row and inserting the new row, let me come back here. I don't remember if I actually still had it. Yeah. In the Kimball archives here, under the year 2008, ironically, I brought this one up, there was a topic here on using the SQL merge statement to populate and to handle slowly change in dimension processing. So actually he gives a brief but meaningful example of using a merge statement to update a customer table based upon incoming data, where we need to retire the old row based upon a change and then insert the new row, which is typically what happens with a slowly change in dimension. You retire the old row with the effective date, and then you insert the new version of the row with the same business key, but it's going to get a new primary key. Again, coming back to my slide deck here, if we have a book whose price changes, say on January the 1st of 2011, we need to retire the old row and put in the end date and then insert a new version of the row, same ISBN number, same book name, but a different price with a new start date. Well, when sales transactions come in, we need to make sure that if we have a sale that was on January the 2nd for that book, we want to write out to the fact table the book PK of 2. So we obviously need to determine what was the version of the book at the time of the sale. So we have to dive into the mention table, not just on the ISBN number, but on the most recent start date that's on or after, or that's on or before the sale date. And if we get a late arriving sale, let's say we had a sale back in back in December of 2010, even though it might be 2011 now. Well, at the time, the book was still under the old price of $49.95, so we'd write out the book PK of 1 to the fact table because that sale was when the book was still under the old price of $49.95. So there's versioning involved, there's making sure that you've got the proper synchronization, and there's the issue of correcting data when you get in a late arriving dimension value, when a price changed a month ago but you're just now getting the data. And again, I've got several notes in the slide deck that cover this, and also Kimball talks about this in the dimension modeling book. But a lot of this is about recreating what the product looked like at that point in time.
Okay, the next one is, what kind of tool would you recommend to build a user interface that can enter data directly into the data warehouse or database? I'm looking for a GUI for the users that don't know SQL.
Okay, want to make sure I understood the first part of the question. The first part of the question was the necessary interface for people to put data into the data warehouse tables. Did I catch that right?
Yeah, directly. It looks like he's looking for a GUI that the users could use who don't know SQL.
Okay, well, typically, let me come back to one of my pictures here. Typically, the data that gets into a data warehouse is going to come from different interfaces that are already established. So if you have region managers putting in budget information, they might be putting it into spreadsheets, and that data is going to be is ultimately going to be sent to corporate, and there might be some ETL process to load data from that spreadsheet into the into the database at corporate. Now, let's say there's new data that comes along. Let's say that you didn't have a budgeting process and now you do. A question is going to come up. If there's no interface in place, what's the best way for these region managers to get the data in? Well, I always hate to answer a question with it depends, but that's going to be one of those it depends. Some clients will build a custom web interface, maybe a custom web page, so the data can be posted directly to some of the data warehouse tables from that web interface. Other people might set up an Excel spreadsheet, or they might actually use an older technology, maybe something like Access, and set up link tables. I actually heard someone talk about that recently, where they use Access, even though it's an older database, it still obviously works, setting up link tables that map directly to data warehouse tables. So that's going to be one of those it depends as far as how people are going to get data into the data warehouse if there's not already a mechanism in place. In most cases, that's going to be the exception rather than the rule, because most of that data already has an entry point either through some legacy application or some existing application that might be new that's dealing with the transaction end. So what's being described, I would think in most environments would be exception rather than the rule. And as far as what you're going to do, some people might build a web interface for it. Some people might just set up a special spreadsheet or maybe a template in Excel or maybe even in Access or some other tool. So I would think it would be something along those lines.
The next one is
that's a very good question.
Should fact tables have circuit keys?
Okay, by coming back to some of the diagrams I had of fact tables, by surrogate keys, I want to make sure I understand something. Fact tables should have the foreign key relationships to the dimensions themselves. Now, if the question was, should a fact table also have an identity column that serves as a unique surrogate identifier for the fact table, independent of the foreign keys, that's actually a topic of debate that I've heard a lot of DBAs and data warehouse people argue about. I'll put it this way. If the granularity of the foreign keys in the fact table, if the combination of product key, order date, due date, ship date, reseller, promotion key, if those are constrained to be unique, if the combination, if the composite definition of the foreign keys would define uniqueness in the table, then you can make the argument that there's really no need, because you've got a composite definition that guarantees uniqueness. However, other people might say, well, if you don't have a guarantee of uniqueness, or maybe you've got an environment where fact tables are maintained across physical boundaries, and you need somehow to bring them together, well, then you've got the argument in favor of having an identity column in a fact table. I've never had any objection personally. If someone wants to put an identity column in a fact table, if for no other reason, just for safety's sake, I've never had any objection to it. I know some purists who kind of grumble a little bit about it. I'm not one of them. So if people want to put it in, if for no other reason, because they're thinking forward that they might need to uniquely identify a row based upon that single value, then it's probably a good idea. Good question.
The next one, he wanted you to, if you could go to the slide to where it's the tabular book. He wanted to see the name of the tabular book.
Yeah, this is a very good one, and it's in the slide. When you get the slide deck at the end here, I've got the link to the book on Amazon. It's by Microsoft Press. It's SQL Server 2012 Analysis Services by Chris Webb, Alberto Ferrari, and Marco Russo. These are three fantastic authors. A lot of times I refer to them as the three wise men of analysis services, because these guys know analysis services in and out. And of all the books on the tabular model, there's some good ones out there. This is the best one that's available. So if you work with a tabular model, you should get this book.
And then how would you store order and order line measures in a fact table?
That is a very good question, because some people will actually store two fact tables. They'll have an order fact table, and they'll have an order line item fact table. So they have two fact tables that are related by the order ID. My preference, if you can realistically do it, my preference has always been to have one flat fact table of line item that's keyed by line item with the order dollars for the line item stored in the table. So my preference has always been to have one flat fact table that's keyed by the order and by the line item. Now, where that gets to be a little bit of a challenge is, let's say you have some measures that are tied to the order. So let's say you have an order with two line items, item A and item B, and you have the order dollars and the unit price, everything like that, tied to the item, so they fit in the fact table very nicely. But then you have something like freight, and maybe freight is on the order level. Well, you obviously can't store the freight twice, because if you go to aggregate it, you're going to run into problems. What you'd have to do in that case is maybe allocate it based upon the size of the two items with respect to the dollars. So if one line item was for $10 and the other line item was for $20, and you had freight of $40, well, then you would obviously carve it up, 1/3 and 2/3 based upon the original dollars of the two items. So my general preference has always been one flat fact table, although I realize that some people will construct it as two fact tables related by the order. But the one problem that my suggestion poses is, if you have metrics that are specific to the order, in that case you've got to allocate them and come up with an allocation method. Some people don't like to go through that allocation method, so they build two fact tables that are tied by the order. Both ways will work. It all depends upon how much additional work you're willing to go through.
Is dimension out outrigger the same as Snowflake?
That's a good question. A dimension outrigger is a special type of a Snowflake dimension. Now, an outrigger is by definition a Snowflake dimension. However, not all Snowflake dimensions are outriggers. If I go back to that, so I'm glad that question came up. If I go back to that one, when I had the product dimension here, let's say that we had made subgroup and group and brand separate tables. So we basically normalized it. That would be an example of what we call a Snowflake dimension. But it's not terribly likely that would be an outrigger because you probably wouldn't have many attributes at the group and the brand level. So that would be a Snowflake, but probably not an outrigger. Now, what makes an outrigger different? Let me come to that one. What makes an outrigger different is because of the large number of attributes for the parent definition, in this case the county to which customers are associated. We have a large number of attributes that are specific to the parent county, not to the customer. So an outrigger is a special type of a Snowflake. So, good question.
Okay, and we just had a few comments from others who were talking about that you don't necessarily want ad hoc adding of data because it could introduce the human errors, and it's hard for the people to correctly enter values on foreign keys.
Well, that is a very good point, and I'm glad that came up. Let me come back. Let me come back to that example. If you've got special interfaces that have been set up to post data into a table, it's a given, and I apologize for the fact that I didn't bring this up. Whoever made the comment is absolutely correct. You would need to have some kind of a control mechanism. If let's say that you build a custom web page for people to put in forecast information, it's a given that the validations that would save the data would need to make sure that they're putting it in for a region or for a market that's valid. The absolute last thing you want to do is get any dirty data. You never want to have dirty data in any system, period, but especially not a data mart because the data is presumed to be clean. So whatever mechanism you set up, it's assumed that you'd have the necessary validations in place. Now, what some people may do as a result of that, let's say that the region managers have some interface to enter data. Well, that data might go to a staging table, and then you might have a separate process that reads the data from that staging table, does some validation checks, and posts the good data to the data warehouse. So yeah, whoever brought up that point is absolutely correct. You need to have the same control mechanisms in place because the whole idea of ETL is to clean data before it hits the destination. So yeah, I'm glad the person brought that up.
Well, Kevin, we'd really like to thank you for the presentation and for going over with the time here, but answering all the questions. I'll send you a copy of all the questions that were posted so you can follow up with those.
Sure.
This recording and the slide deck will be posted to the past DBA virtual chapter to our archive page. And
Okay.
just give us a day or two, and that will get posted up there for everyone to re-listen to, look at the slides, get the names of the books if you've missed them.
Okay.
But I wanted to thank you again for a great presentation.
Sure. Thanks. Thanks for having me, and be happy to come back in the future. So thanks everybody for attending.